Hi everyone! In this video, we're gonna calculate the work done by pulling a rope to the top of a building. A 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? And how much work is required to pull up only 20 feet of the cable? So for these types of problems, you need to know two formulas. So the first formula is for the scenario when you're pulling the entire rope to the top of the building, and the work can be calculated using the integral from 0 to the end of the rope of W, which is the weight, times Y of d of y, where W, or the weight, is equal to the total number of pounds, or the total number of pounds here, divided by the total number of feet. For the second case scenario, you're pulling the rope partially by d feet. So if the rope is 100 feet long, you're not pulling the whole thing up, you're only pulling, like, let's say 20 feet or 30 feet up, so partially by d feet. In this case, the work can be calculated using the integral from 0 to d of w times y times d of y plus the integral from d to the end of the rope of w times d of y. So go ahead and pause this video and write down these formulas, and I'll show you how to use them in this problem. The first step is to draw a diagram. So we have a building right here, and we know that the rope is 100 feet long, and the rope is hanging on top of the building. So our person here is going to pull up the rope to the very top, and we know that the length is 100. We also have a y-axis pointing down, and let's just say that this direction is positive because it's easier to do that. So question A is asking us how much work is required to lift the cable to the top of the building, and that looks like case scenario 1. So for the first case scenario, we can use these formulas, and we want to find the unit weight first. So the unit weight is equal to the total pounds, which is 200 pounds. So 200 pounds divided by the total feet. 200 pounds divided by 100 will simply give you 2, and the unit is pound over feet. Now that we know the W, we can substitute it into this formula to calculate the work. So work is equal to the integral from 0 to the end of the rope. And the end of the rope is here, which is 100. So this right here will be 100 times W. W is 2 times Y. And don't forget the d of y. Now this is equal to 2 times the integral from 0 to 100 of y times d of y. And we moved out a 2 because it's just a constant. This will simply be equal to 2 times the antiderivative of y. And that is 1 over 2 times y to the power of 2. And the limit is going to go from 100 to 0. This is equal to 2 times 1 over 2 times 100 to the power of 2. So we're just substituting these numbers into the formula, minus 1 over 2 times 0 to the power of 2. This is equal to 2 times 1 over 2 times 100 to the power of 2 minus 0, because this right here is just 0. So minus 0, and close the bracket right there. We can simplify this, saying that this is equal to 2 times 1 over 2 times 100 to the power of 2 is 10,000. So this is 10,000, close the bracket, and we also know that 2 times 1 over 2 will cancel out, which leaves us with 10,000. So this number right here has the unit of feet-pounds. That's the unit of the work. And 10,000 is the amount of work required to pull the cable to the top of the building. And that's the answer for part A. The second part of the question asks us about the amount of work required to pull up only 20 feet of the cable. So we have redrawn our diagram, and this time we only want to pull up 20 feet. So we want to pull up from here to here. We're only pulling this side up. Now this looks like it belongs to the second case scenario. And since we're pulling the rope partially by d feet, which is we're pulling by 20 feet, so d in this case will be equal to 20 feet. To calculate the work, all we need to do is use this formula. So the work is equal to the integral from 0 to d, which is 20, times w, and w is 2 as we found earlier, times y, d of y, plus the integral from d to the n. So d will be 20, the n will be 100. So this will be 100 times w, which is 2 again, times d, and d is 20. So careful here. This is 20 of d of y. This is equal to the integral from 0 to 20 of 2 times y times d of y, plus the integral from 20 to 100, and 2 times 20 will give you 40 d of y. Now let's go ahead and move these constants outside of the integral. We're going to have 2 times the integral from 0 to 20 of y d of y, plus 40 times the integral from 20 to 100. And what's going to be left in here? Well, it's just going to be 1 d of y. Now, why is it 1? Because you can rewrite this as 40 times 1. Right? So when you move the 40 outside, then all you have left is just 1. This is equal to 2 times the antiderivative of y. And the antiderivative of y is 1 over 2, as we know, times y to the power of 2. And the limit goes from 20, this is 0, plus 40 times the antiderivative of 1. And that's just going to be y. The top limit is 100. The bottom is 20. This is equal to 2 times 1 over 2 times 20 to the power of 2 minus 1 over 2 times 0 to the power of 2. And over here, we're going to get 40 times 100 minus 20. This is equal to 2 times 1 over 2 times 20 to the power of 2 is 400. So 400 minus 0 plus 40 times 100 minus 20 is going to be 80. So this is equal to 2 times 200. This is 200 plus 3200. And so this is equal to 400 plus 3200. And we get 3,600 feet-pound. So this number right here is the amount of work that it takes to pull up the cable by only 20 feet. Let's do another problem. A heavy rope, 50 feet long, weighs 0.5 pounds per feet and hangs over the edge of a building that is 120 feet high. How much work is done in pulling the rope to the top of the building? And how much work is done in pulling half of the rope to the top of the building? So go ahead and pause this video and try this one yourself, and then you can double check your work with me. So we have our diagram here, and we know that the rope is 50 feet long. We also know that the building is 120 feet high. So from here to here is 120, but we don't actually use this number in the formula. So how much work is done in pulling the rope to the top of the building? Well, this looks like the first case scenario. So the work is equal to the integral from 0 to the n times w y times dy. Now we know what w is because they gave us 0.5 pounds per feet. So notice the unit right there. And because of that, we know that the weight unit is 0.5 pounds per feet. Or we can also write it as 1/2 pounds per feet. The end of the rope will simply be 50, so we can replace this with 50. Since 1/2 is a constant, let's move it outside of the integral. So we have 1/2 times 0, 50 times y dy. This is the same as 1/2 times 1/2 times y to the power of 2. This is 50 above, 0 at the bottom. And this is equal to 1/2 times 1/2 times 50 to the power of 2 minus 1/2 times 0 to the power of 2. This is the same as 1/2 times 1/2 times 2500, because 50 to the power of 2 is going to be 2500 minus 0. So we end up with 1/4 times 2500, which is the same as 625 foot-pounds. So this number right here is the amount of work that it takes to pull the entire rope to the top of the building. Now, what if we pull half the rope to the top of the building? So if we're pulling half of the rope, then we're actually pulling it up by only 25 feet. This is the second case scenario. So the work formula will be work is equal to the integral from 0 to d. And in this case, we're pulling it up by only 25 feet. So d is the same as 25 times w times y. Now we know that w is 0.5, so let's just write 1/2 times y instead. And don't forget the dy. Plus the integral from d, so from d to the n, remember the formula, right? So d is 25, the n is 50, so that's the end of the rope, which is 50, times w, which is 1/2, times d, and d is 25. So this is times 25, and close the bracket, d of y. Now 25 times 1/2 is the same as 25 divided by 2. Now let's move the constants outside of the integrals. We get 1/2 times the integral from 0 to 25 times y, d of y, plus we move this outside, so we get 25/2 times the integral from 25 to 50, and it's 1 in the inside. So this is the same as 1/2 times the antiderivative of y, 1/2 times y to the power of 2. And the limit is 25, this is 0, plus 25/2 times the antiderivative of 1, it's just y, and it's 50 and 25. So we're gonna get 25 times 1/2 times 25 to the power of 2 minus 1/2 times 0 to the power of 2 plus 25/2 times 50 minus 25. Now we're gonna get 1/2 times 1/2, and 25 to the power of 2 is 625. And we minus 0, so we can just close the bracket right there. Plus 25 divided by 2 times 25. Now we can rewrite this as 25 to the power of 2 divided by 2. And like I said before, 25 to the power of 2 is the same as 625. So we can write this as 625 divided by 2. Now 1/2 times 1/2 is simply going to be 1/4 times 625 plus 625 divided by 2. So this is the same as 625/4 plus 625/2. This is equal to 625 divided by 4 plus 1250 divided by 4. 625 plus 1250 is same as 1,855 divided by 4. And if you put this into a calculator, you're gonna get 468.55. So I'm looking at my notes here, but basically this is the same answer as the one you find in the textbook. So the unit is gonna be feet-pounds, and this number is the amount of work that it takes to pull up the rope, half of the rope, to the top of the building. So this is the answer to question B. Let's do one last problem. A cable that weighs 2 pounds per feet is used to lift 800 pounds of coal up a mine shaft that is 500 feet deep. Find the work done. So go ahead and pause this video and try to find the answer, and I'll give you the answer in a moment. We need to find the amount of work that it takes to pull up the rope, and then we find the amount of work that it takes to pull up the coal. So at the end of the day, work is equal to the work that it takes to pull up the rope plus the amount of work that it takes to pull up the box of coal. And let me show you how to calculate the work. Now we know that the mine shaft is 500 feet deep. So the distance from here to here is 500. Now the work of the rope, since we're pulling it all the way up, is the first case scenario. So it is the integral from 0 to the n of w times y times dy. And the n is basically 500. So the number up here is going to be 500. It's 0 here. And the weight unit is something that the problem has given us. And it's 2 pounds per feet. This is 2 times y dy. So let's move the number 2 outside of the integral. And we get 2 times the integral from 0 to 500 times y dy. It is equal to 2 times the antiderivative of y. You should know this by now, is 1 over 2 times y to the power of 2. On top is 500, the bottom is 0. So we get 2 times 1 over 2 times 500 to the power of 2 minus 1 over 2 times 0 to the power of 2, and close the bracket right there. This is equal to 2 times 1 over 2 times 500 to the power of 2. That's going to be 250,000. And finally, 2 times 1 over 2 are going to cancel out. And we're left with 250,000 foot-pounds. So foot-pounds. And this is the amount of work that it takes to pull the rope to the top, right? So this is only for the rope. We are so close to finishing. So let's find the amount of work that it takes to pull up the coal. And one thing I should have written here is this is the total work. So the total work to pull both things up. So what's the amount of work that it takes to pull up the box of coal? Well, remember, the work formula is just force times displacement. So if you're not pulling up a rope, you use this formula. And the work to pull up any object that is not a rope, it could be a box, it could be a truck, it could be a piano. The amount of work that it takes to pull it up is force times displacement. So what's the force? Well, force is in pounds, right? Force is in pounds, and the coal is 800 pounds. So pound is a force times the displacement. And the displacement is the distance from here to here, and that's basically 500 feet. So 800 times 500 is going to be 400,000. And notice that the unit makes sense here. So the unit of the work is in foot-pounds. And this number right here is the amount of work that it takes to pull up the box of coal to the very top. Last but not least, 250,000 plus 400,000 is going to be 650,000. And the unit will be in foot-pounds. So this number right here is the final answer. And this number represents the total amount of work to pull up not only the rope, but also the box of coal to the very top of the mine shaft.